Hi everybody, welcome to my channel Rao's Concepts of Physics Learning the Unlearned. Today I am going to explain the concepts based on Coulomb's law and its failure and where we can apply this Coulomb law. And before going to the Coulomb's law, I am going to give just brief details about electric charge, and everyone should know before going to that what are the different properties of a charge. Suppose the charge, whatever the charge, we will talk in this electrostatics. So it is scalar in nature, means only magnitude will consider, no direction. And units of this charge will be Coulomb. And coming to types of charges, so you are having two types of charges. One is positive charge and another one is negative charge. And coming to the quantity of this charge, so as you all know, the charge of electron or proton, if you take 1.6 into 10 power minus 19 coulombs. And coming to the next point, very important, is the electric charge is quantized. So that means what is the meaning of quantized? If any physical quantity, if you are able to represent that physical quantity in integral multiple of something, suppose in this case charge, here is the charge of electron, which we can always represent it as an integral multiple of charge. That means here n is equal to 1, 2, 3, it will so on. That means the electric charge can be represented an integral multiple of 1.6 into 10 power minus 19 coulomb. So that's why we call electric charge is quantized. And coming to the next point, electric charge is conserved. So that means what is the meaning of conserved? That means it is neither be created nor destroyed. Any physical quantity neither be created nor destroyed. So it will transfer from one place to another place. The same thing you can apply for this electric charge also. So best example we can take as radioactive decay of uranium. Suppose if we are having uranium 92 to 38. So during radioactive decay it will decompose into thorium 90 to 34 plus 2He4. So that means when uranium 92 to 38 is undergo radioactive decay, it will split into thorium and this one. And if you see here, this is the charge of uranium 92, and even after the radioactive decay, so 90 plus 2. That means the total charge before the radioactive decay and after the radioactive decay is similar. That means the charge is neither be created nor destroyed, it is just redistributed, that's all. So that's why electric charge is always conserved. So these 2 points are very important. Electric charge is quantized and electric charge is conserved. And coming to one more important point is, when any charge is moving, that means accelerated charges will produce energy. And one important point here regarding the charge is, whenever you place charge, suppose you take a conducting sphere, I am telling this is the conducting sphere. So if I put some charge E at center, so when this sphere is conducting, so whatever the charge you keep, wherever you keep, it will move to surface. That means in case of conductors, charge always resides on the surface. Whereas if you take insulator, suppose this sphere is made up of some insulating material and I am putting charge here somewhere here. So that means, so your charge will be localized only to this particular point. It will not go anywhere. So whereas in case of conductors, wherever the place you put your charge, it will move towards your surface and it will reside on the surface of the conductor. And This is the normal point. If you take charge, so charge cannot exist without mass. That means if you have some mass particle, so and charge will be distributed over that particle. Suppose if particle is not there, so your charge cannot exist. So that is the meaning of this point. And now coming to the main topic of this is Coulomb's law. So Coulomb's law, first briefly we can explain between two charges. That means it is similar to your gravitational force law, but here this Coulomb's law is explained to charges and charge distribution. So here I am showing two spheres Q1 and Q2, two charges Q1 and Q2 separated by a distance r. That means your two charges Q1 and Q2 separated by a distance r. So now depends on the charges, whether these two charges are positive or negative, or one positive one negative. So there will be always some force existing between these two charges. Either that force be repulsive or attractive, that depends on the nature of this charge. Whether it is positive, both are positive, it is repulsive force. If both are negative, it is repulsive force. If one is positive and another one is negative, you will have an attractive force between these two charges. And how you can get that force between these two charges? So this is just as similar to your gravitational law. The force between two charges is always directly proportional to the product of these charges, like this. F is directly proportional to Q1 into Q2, and your force is again inversely proportional to square of the distance between these two charges. And one important thing is, while measuring the distance between the two charges, you should consider from this center of this charge to center of this charge. You should always take center of the charge as your starting and ending point. And you all know that you can combine these two equations so that you will get F is directly proportional to Q1 Q2 by R square. And in order to remove this proportionality constraint, we can introduce some proportionality constant here. So this value is nothing but your 1 by 4 pi epsilon naught Q1 Q2 by R square. So that means your proportionality constant is 1 by 4 pi epsilon naught is your proportionality constant. So in general, if you substitute all these values, 4 pi is equal to 3.14 and epsilon naught, that means permittivity of free space, which is equal to 8.85 into 10 power minus 12. If you substitute all these values, you will end up with a value of 9 into 10 power 9. So 9 into 10 power 9 value Q1 Q2 by R square. So this is your either it is repulsive or attractive force between these two charges. Now what will happen, as I mentioned here, one important thing is here epsilon naught is permittivity of free space. That means now, so the medium present between these two charges is, if it is air, so it is nothing but this one. Suppose if you are placing these two charges in between some medium, suppose in that case your formula can be transformed into F is equal to 1 by 4 pi epsilon naught k, this is small k, epsilon naught k, Q1 Q2 by R square. So here, so you can replace this epsilon naught k with an quantity epsilon, so then your equation will be transferred into 1 by 4 pi epsilon Q1 Q2 by R square. So here this epsilon is nothing but permittivity of your medium which you are placing in between charges Q1 and Q2. So that means here you are having two different formulas for your force exist between two charges, 2 point charges. So here one is 1 by 4 pi epsilon naught Q1 Q2 by r square, which is in case of free space, and another one is F is equal to 1 by 4 pi epsilon Q1 Q2 by r square when you are placing charges in some medium, where epsilon is permittivity of that particular medium. Now we will see in detail how these forces will act on each other. It depends on the nature of the charges, and that I am going to explain here. Suppose you are taking two charges, here I am considering both are positive charges, that means this is positive and your Q2 is also positive. Now we will write the forces acting on each other. Now if I write force acting on Q1 due to Q2 is always in this direction. That's why, because both are positive charges and the force is repulsive. So that's why the force acting on Q1 due to Q2 is your F12, which is directed in this way because both are positive. It is a repulsive force. And the unit vector corresponding to this is represented in this way. So that means your R12. That means your unit vector R12 is in that direction. That means which is in this direction. This is your unit vector. And in a similar way, the force acting on Q2 due to Q1 will be away from this charge, which is nothing but your F21, and corresponding unit vector will be in this direction, R21 cap. So this is the distribution of how the forces are acting on each other when both are similar charges, whether it is positive charge or negative charge. Now from this you can clearly see that your unit vector R12 cap is opposite to R21, that I can write it as R21 like this. So in a similar extent you can take like this, you can write in terms of forces F12 is equal to minus of F21. So that means your forces are opposite. That means whenever the force is acting on this, which is exerting force on Q2, so that means which is similar to your Newton's third law. So the similar situation you can explain how the forces are directed when both are different charges. That means your Q1 is positive, now your Q2 is negative. That means you are having one positive and one negative. That means you will have a attractive force between these two charges. Now the force acting on Q1 due to Q2 is in this direction because it is attractive force, your F12, and the corresponding unit vector will also be in this direction, unit vector. In a similar way, the force acting on Q2 due to Q1 is F21, and corresponding unit vector will be in this direction. So even in this case also you will have a situation like this. That means F12 is equal to minus of F21. So this is how the forces acting on each atom, each charge, when both are positive charges and one is positive and another one is negative. And hope you all like my video, and if so, please subscribe my channel and hit the notification bell for any updates. Thank you.